So what is this, our 5th lecture in vapor power cycles? We've covered the Carnot, we've covered the Rankine, we've talked about the enhancement superheating, talked about the enhancement reheat, we've talked about regeneration, and we've covered the open feed water heater. Well, today we'll talk about the closed feed water heater. So when you have regeneration, what you're trying to do is preheat the water that goes into the boiler or steam generator, different applications, different names for it, but that's where the heat is added. If it comes in really cold, then a lot of heat is brought into the working fluid at low temperature, bad for performance. Bring as much of the heat in at high temperature into the working fluid. So you preheat it. One is open feed water heater, which is very basic. It's just mixing. You just have some warm or hot steam or fluid. You mix it with what typically comes after a pump. After a pump, it's very cold, such that this is warmer. And if it's mixing, what about the pressures? They're all the same. They're all the same. It's just mixing. So usually this is at some intermediate pressure. You have to put it through another pump. So we have pump 2, where before we just had pump 1 to boost it, then take it into the boiler. All right, but this, just mixing. Just mixing. But what you can do is you can have what they call a closed feed water heater. So you have an in and an out and an out. So you have 4 fluid streams. Well, the one fluid stream coming here is the hot fluid stream, and it goes that way. And often it comes in at some superheated vapor or saturated vapor or high quality steam, and it condenses. And as it's condensing, the condensate collects at the bottom, and then you have to do something with the condensate. But when you condense steam, there's a lot of heat transferred out of it to condense it. It's transferred to the colder fluid that goes in and out. And as it's shown here, we would talk about the fluid flowing in the tubes and the fluid flowing in the shell of this shell and tube heat exchanger. You're going to get to heat transfer. You may be already in it. Maybe you've already passed it. I don't know. ME4313. Anybody in it? Couple people? You're going to get the hopefully shell and tube heat exchangers. So here's a good example of it. So on the shell side, the steam condenses on the outside of the tubes, drips, falls to the bottom, the condensate collects, and you have to do something with it. So this would be the cooler fluid or cold fluid going through the tubes. Well, this is a funny name for something, isn't it? Just like this regenerative vapor power cycle, that word is a little funny. It takes us a little getting used to. What do they mean by it? This is a steam trap. If you were the first person to identify it or give it a name, maybe, or if I would have been the first person, I would have said it's a steam police. Right? What do you mean by police? The ones out there directing traffic. Think of it as they monitor how much condensate builds up, and then, okay, now a bunch of you can go through the condensate. Go through. But then as the line gets smaller, the condensate, then the steam trap stops and waits until more condensate builds up. There's a number of different designs. You can go to the internet, YouTube, look at videos. Companies that manufacture these put out really great videos to describe how they work. I just don't think I have enough time to really spend time going into it. Most of them in steam power systems have been around so long, it's a very mature industry making steam traps. A lot of engineering design has gone into them. They also make them such that they can get rid of the non-condensables as well. Let's get a little air in there. It doesn't condense like the steam. Where is it going to collect? Where steam condenses. So you've got to get rid of the air out of the system. So, but anyway, the steam trap lets it condense, and only condensate comes out. Every now and then these steam traps will fail. Anybody have an automobile had a water pump fail? power steering pump fail, transmission fail, engine, I mean, these things, they work great, but then just like in a power plant, you get devices that fail. And when the steam trap fails, guess what it does? Usually it fails where it's all open or all closed. And if it's all closed, something's going to give very quickly, and something's going to happen where you can't operate the facility very long. But they often will fail in the open position, and then it's really hard to detect. And they'll be letting actually vapor through when they should only let liquid. It'll be not as efficient. So there's a lot of engineers that work doing inspections of different facilities and plants, and they're experts at being able to detect this box called a steam trap. Can I tell if it's, failed or not? Which way is it failed? Is it stopped, plugged, or is it open all the way? Anyway, let's press forward. So we have these complicated systems. Last time we were analyzing this one with an open feed water heater. I don't think I was able to explain everything about this, so let me kind of wrap it up. The goal was to get the fluid that comes in warmer. True? If you didn't have it, it would just take this fluid right here. For the numbers, think about 60 degrees C, that's at 20 kilopascal condenser pressure, and put it in. But if you put a little open feed water heater, divert some fluid down after the first turbine stage, you can pick it up, bring it up to about 180 degrees C. State 7 and State 8 have about the same temperature, even though the pressure has been boosted in that second pump. That's quite an improvement. And then for our numbers, it gets up to around, the boiling point was around 295 degrees C, goes from saturated liquid to saturated vapor, and then we were superheating it out to 440 degrees C for this problem. And what we found was by moving it from 60 to 180, it reduced from 5% of the heat input was just to heat the water before using the open feed water heater. Now it's reduced to 22%. And that's pretty good. That's a good improvement. So that it didn't really change the backwork ratio much, but it does improve by a point or two, 1% or 2, the thermal efficiency of the cycle. All right. I can't remember, did I describe why in this table for all of the transfers I have 2 columns for Q and 2 columns for the work? And both of those have the same units of kilojoules per kilogram. Did I describe that? Well, we have some fluid that's diverted, and this Y right here for this problem is around 20%. Around 20% is diverted down to feed it, meaning 80% continues in the loop. 1 minus Y is about 80%. Well, when you do a net, Q net and work net for the cycle, and you're working with the preferred per unit mass, so kilojoules per kilogram, what you want is you want to be talking about the same per kilogram, and it's common to put that kilogram, everything on the basis of what goes through or enters the first turbine. So I use a little asterisk. I don't think the book does this, but I have Q for what goes through the device, and work what goes through the device per kilogram what goes through the device, and then I adjust it for back to what went through the first turbine. Now, when you're looking at this first pass through the boiler, there's no difference between heating it up and getting it, boiling it, and superheating it. So these two numbers are the same. And if you look at what goes through the first turbine, well, that's kind of obvious. The work is the same. This work with or without an asterisk the same. But when you go to reheat, notice there's 602 or 1.7 kilojoules added per each kilogram that goes through the reheat right here. But when you weight how many kilograms go there compared to what goes through the first turbine stage, It's only 478.6, and that's the number that we really want. When we sum the Q's in this column, we get Q net, which is how much heat is added into the cycle per kilogram entering the first turbine. And if you do the same for the work, you'll notice the work through the second turbine per kilogram going through the second turbine is high, but per kilogram going through the first turbine is a lot lower. But when you get it all on the same per kilogram basis, you add them up, you'll get that these Q net and work net match. They're the same. Where compare, if you just said, oh, per kilogram going through the device, you would say, I have an error somewhere. Well, yeah, because the same kilogram doesn't go through each device. It splits after the first turbine. Is this obvious? Have you solved enough problems already in the homework to do this? All right. So let's continue on then. So what about this closed feed water heater? Well, we have the hot stream and we have the cold stream. And let's talk about some things here. We already talked about that steam trap. Let's talk about pressures. What is the pressure at 6 compared to the pressure at 2, the pressure at 8, and the pressure at 7? Is pressure at 6 equal to the pressure at 7? But is it equal to 2 and 8? No. And so these two pressures, pressure 2 and 8, are the same, but then they're different. That's the beauty of having this closed feed water heater, is you really don't need another pump. What comes out of it, if it's high enough pressure, is ready to go into the boiler. All right. So when you work with these, you look at the pressures first. All right. This is Y, the fraction, which is diverted to feed the closed feed water heater. Can you get an expression for Y in terms of enthalpies? You know, somebody says, for this problem, it needs to be 18%. No, it needs to be 20%. How do we determine 18 or 20%? How do we get that equation for Y? Can you do that? We did it last time, so in the interest of time, should I just press forward? How do you do it? Tell me in words and then I'll do it. Do a mass balance and an energy balance. True? Okay. So let's do this. Let's do our mass flows, and I'll do it through the whole system. And so 100% goes into and through the first turbine. Then we split, and Y comes down. That would be like 20%. We're going to find the value of Y in a second, the equation for it, but think about what continues over to reheat. 1 minus Y. What goes through reheat? 1 minus Y. What goes through the second turbine? 1 minus Y. It's like 80% or 75%. What goes through the condenser? 1 minus Y. But notice the condenser also has an input from the steam trap. So if Y goes into the hot side of the closed feed water heater, what is coming out and going through the steam trap? Y. So Y is also coming into the condenser in a different pipe inlet. So what comes out and goes into pump? It's back to 1, isn't it? So be careful there. It's back to 100%. 100% goes through the cold and then continues on. 1 goes through the first pass of the boiler. All right. Now that's all our mass balances. I know it may be a little abstract, but after you do a couple of these, it's like, oh yeah, that makes sense. Now we do an energy balance. And we're going to do an energy balance for a control volume around that closed feed water heater. And I encourage you to do it at your own pace and do it with your own equations. Go back to the most fundamental energy balance equation. But you're eventually going to get that what comes out of that hot stream, which would be Y times enthalpy 2 minus enthalpy 8. Won't H2 be greater than H8? Won't that be what comes out of that fluid stream?
I think you may have already answered this, but why is there not a pump after the closed feed water?
Oh, because this pump can boost it all the way up. So the pressure at 6 and the pressure at 7 are the same, and the pressure at 1 is the same. That's all the high pressure, right? And so, you know, if you think about it, Steam traps are cheap compared to pumps. So there you go. You can just put a simple steam trap in. So this is what comes out of that hot fluid stream, and it goes into, one is the mass flow rate type of times the enthalpy 7 minus enthalpy 6. The equation of Y is equal to H7 minus H6 divided by H2 minus H8. Do you agree? Give me a thumbs up. You agree? Look good? Yeah. Professor, are we going to memorize these equations for the exam? No. You're going to know how to rederive it. Maybe I change up the state numbers. Maybe, I give it a different numbering system and just adapt it a little bit. You should be able to do a mass balance and an energy balance and come up with the equations for what is needed to be diverted. Okay, now, this is a subtle but tricky concept here. Is what is the condition of the state 5 coming into the pump? How do we describe it? It's after the condenser, before the pump. How do we describe that what's coming into that pump? Saturated liquid. That's our happy state for feeding pumps. Okay. Now, what is state 6? Give me a brief description of state 6. Saturated liquid? Compressed liquid. It's compressed liquid. Now this will throw a lot of students for, a challenge. We're going to talk about state 7 in a second. That's the hard one. We've got now state 6. That's pretty easy. We know that it's compressed liquid. All right. What about state 2? What typically is the condition of the steam at state 2, which is diverted down to this closed feed water heater? High quality, maybe slightly superheated, but it's very nearly, just say high quality. High quality steam. Could be slightly superheated. What is state 8 coming out the bottom? Saturated liquid, isn't it? Isn't it saturated liquid? Saturated liquid. All right. Now, we already talked about the pressures. But here is the real challenge. What is the description of state 7 coming out of that closed feed water heater? And yes, you have the tools and the knowledge to make a good assessment of that, although it may take you more time than I have in this lecture to let you do it on your own. So I'm going to give you 2 minutes to think about it, and then I'm just going to give you the answer. I feel like I'm cheating your education. All right, so what really is helpful with this is a TS diagram. And on a TS diagram, it's good to get all your pressures and then start thinking about temperatures and what's happening as it flows through the system. Now, this illustration, I need to go to a TS diagram. Do you have this illustration down? Have you seen enough numbering, state 1, 2, 3, 4, 5, 6, and all that? So let's go look for a TS diagram. I know I have one. Oh, make me a liar. There we are. So it comes out of the boiler superheated, 8 megapascal, 440. It's right around there. That's state 1. It goes through to 2 megapascal or 1 megapascal. I can't remember. Let's say it's 2 megapascal. Right there is state 2. Going to get reheated to 440. That would be state 3. Goes down to maybe 20 kilopascal. State 4. Condense over to state 5. That's what goes into the pump. State 6 is so close to 5, I'll just put an arrow there. But what is the pressure of state 6? Is it the 2 megapascal or 8 megapascal? It's all the way up to 8 megapascal. All right. Now, 2 is diverted over and it comes out of the bottom of that closed feed water heater as saturated liquid, right? At 2 megapascal. That number, that state was state 8. So where is state 8 on this diagram? Saturated liquid coming out of the closed feed water heater So is it right there? State 8. Yes? It's 2 megapascal saturated liquid. What is the temperature coming out? Oh, I don't know, 200 and something. All right, let's go back and look. I'm sure I have some numbers on this. Did I give a problem? All right, fine. I didn't give a problem yet. Anyway, all right, there's state 8. After state 8, the saturated liquid is at 2 megapascal. It's got to be reduced in pressure through the steam trap, which is just an expansion valve controlling, only letting liquid through, to the 20 kilopascal. So where is state 9 on this diagram? And then the last one, so here it is. Find 9 and 7 on this diagram. I'm going to walk around. All right, I'm going to put these states on there. We need the state 7 and state 9. Let's go back to our illustration. So let's talk about this. What's happening between 8 and 9? If I do an analysis of the control volume around the steam trap, I have in at state 8, out at state 9. That looks to me like it would be isothermal expansion. No. Isochoric expansion. No. Isobaric expansion. No. Isentropic. I'm running out of things now. What is it? What is constant from the inlet to the outlet? I said isothermal, T8 equal to T9. True or false? False. I said isobaric. That would be like pressure 8 equal to pressure 9. True or false? False. Isochoric. That would be like the specific volume of 8 equal to the specific volume of 9. False. I'm running out of things here. Isentropic. S8 equal to S9. False. It's irreversible. Highly irreversible. Right? A lot of entropy is generated in the sparse expansion valve. All right. So what is H8? Isenthalpic. Isenthalpic. Is it an isenthalpic process? I need my equation sheet. Come on now. Is it isenthalpic or not? Yes. And then what do we know about this entropy at 8 versus 9? It goes way up. 9 is a lot higher. So if we come over to our TS diagram, S9 needs to be like over here, and it's at that low pressure, and so there is roughly artistically where state 9 is. It's at the low pressure, 2-phase, with some intermediate quality. Okay? All right. That was where state 9 is. Now, let's think about this device called this closed feed water heater. You have the hot fluid going through. You have the cold fluid going through. The temperature of the hot fluid and the temperature of cold fluid, you're always transfer heat from the hot fluid to the cold fluid. True or false? All right. Now, I know that those that have taken heat transfer and know about heat exchangers have an advantage, but can you ever get this temperature at 7 to come out greater than 2 or 8? No. Nope. Think about it. Well, what you could do is if you assume that the temperature at 7 comes out a lot higher than the temperature at 2, you could do a second law analysis and figure out that sigma dots less than 0 in that closed feed water heater. That would be a super design, wouldn't it? To have entropy destruction? Or would it be where you say impossible? Yeah, it's impossible. But a lot of times things that violate the second law of thermodynamics are kind of like scratch your jaw and just look at it and say, isn't that obvious? Isn't that obvious that it's not going to work? So if we throw around some temperatures here, let's see, what would be the temperature at state 2? Temperature at 2, I said, was a little over 200, 205. Do you think, and some people, the classic error is, they'd say, well, it's all the way up here at 8 megapascal, and I think it's coming out saturated liquid. I think state 7 is right there. Oh, it's up to 300. So you had a fluid stream that came in at 205, went out at 205, and was able to heat up fluid to over 300. Or near to 300. You think that's kind of obvious it's not going to work. So this is a classic error to put state 7 up there. But you know state 7 is on this 8 megapascal line. But where does the line go? Right through there. So guess where state 7 could be? Right next to 8, and it's right there. Now it could be a smidgen less. That makes more sense. Maybe it's a little less here. If it's a whole lot less, get a better heat exchanger. You could have done better. True? All right. So, but the best for 7 would be at the same temperature as the saturation temperature at state 8, which I think we said it was a little over 200, 205 or something. Does that make sense? So there's your states on that diagram. All right, let's press forward. You can get a more complex system. True? What do we have in this system? We have an open and we have a closed. How many pumps? Pump 1, pump 2. How many states? It looks like we have up to 13 states. Can you do me, think about this. If you're going to make a table of properties, you're going to think about all of the pressures at state 1, 2, all the way down to 13, right? And there's really, how many unique different pressures are there? We have 3 turbine stages. You're going to have the highest pressure coming through this boiler. The lowest pressure is in the condenser. So at least we have 2 unique pressures. How many other unique pressures do we have? How many unique pressures total in this system? 4. You're getting good. Can you make a list and say, okay, P1 is equal to blah, 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 blah. And then what is the low pressure? P6 is equal to like P7, blah, blah, blah. And then pick out the 2 intermediate pressures and list them all. Can you do that? Get your pressure straight. Once you get your pressure straight, it helps a lot. It's a great exercise. Strongly encourage you to do it. Interest of time, let's just do the high pressure. So P1 is equal to P11, true or false? P10? Is there any other state that has the high pressure, the boiler pressure, the highest pressure? There's 14? Oh, there's no state. Well, okay. Those are intermediate, sorry. They're just help diagnose what's happening going through the boiler. But you're right, 14 and 15. But let's press forward. So the next pressure, the next high is P2. Right? So what's P2 equal to? P3? Is it also equal to 12? That's this pressure down here. Is it also equal to 13? No. What's the next intermediate pressure? P4. Is that equal to P5? Yep. Is that equal to P6? No. All right. 4. Is it equal to 13? P13? Yeah. Pressure at 8. I've put it in order. Let's put 8. Pressure at 9. Pressure at 13. All right, and then let's take a look at the lowest pressure coming out, going into the condenser, 6 and 7. Any others? And if you do a quick sum, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's how many states I had. I pretty well figured them out. That's really helpful to do that. Now, the other one is where do we have saturated liquids? Saturated liquid. And 9, saturated liquid. Where do we have compressed liquids? After the pumps. So compressed liquid, how about 10? Compressed liquid, how about 11? Compressed liquid, we just did that one, isn't it? Compressed liquid, right? All right. Where do we expect probably two-phase, high quality? 2, 4, 6 are probably two-phase, high quality. All right. In state 1, superheated. State 3, superheated. State 5, superheated. They're all superheated vapors. That's probably what we got. What about 12? Saturated liquid. What about 13? Two-phase. Liquid vapor. Some liquid, some vapor. You're absolutely right. Did I get all the states to kind of know where they're at? And we could draw a diagram and put all those states on there. But what I want to do is I want to get an equation for y1 and y2. Well, I know that y1, sometimes I'll write it as y prime or y1. And then y2 is y double prime, or the prime prime. Okay, so that's the same thing. Okay, y1 or y2. How do I get an equation for y1 and how do I get an equation for y2? Mass balance and energy balance. And now we can, and it'll all be in terms of what property? U's, internal energies, S's, entropies, H's, enthalpies. These equations will be in terms of H's, enthalpies. Should I give you a minute and ask you to get the equation for y1? We just did that, Professor, didn't we? All right. But before I get the equation for y1, what is the definition of y1 in terms of some mass flow rate divided by some mass flow rate? Y1, would it be, what is the mass flow rate in this pipe coming down to feed the closed feed water heater compared to what went through or into first turbine? What went into the first turbine went through the first turbine. So we say entering the first turbine stage. Okay, now the next one, this is really hard. Y2. I can see two good definitions of Y2. It would be, what is the mass flow rate coming down this pipe right here to feed the open feed water heater? M dot open feed water heater. Put that in the numerator. You know what? For both definitions, it'll be the same. No distinction there what should be in the numerator. But I had two options for what should be in the denominator for Y2. Should it be the mass flow rate that went through the first turbine stage? Or should it be the mass flow rate that went through the second turbine stage? I'm going to pause, walk around, and see what you think. All right, last time I talked about this funny wording in a problem statement. Sometimes they'll ask a question, they'll say, give me the rate of heat transfer in the condenser in kilojoules per kilogram, but that kilogram isn't per kilogram of steam going through the condenser. Oh no, it's per kilogram of steam going through the first turbine stage. Do you remember that? Last time? Yeah, last lecture. It's this most awkward wording. You know, it's like, why is it not per kilogram of going through the condenser? You've got to link it back to a common denominator. It's per kilogram going through something, and they pick the first turbine. All right? So, which one do you like? True? Yeah. All right. Now that we know the definition of these Y1 and Y2, Y1 you'll be able to work out to be H11 minus H10 divided by H2 minus H12. We did that. True? But can you work out the equation now for Y2? And I almost need to clean up the illustration. It's a little confusing, isn't it? Should I clean up the illustration? Yeah, maybe so. Let's try this. Edit. Now give me the equation for Y2, this one right here. In terms of what? The enthalpies. We know the definition of Y2, do we not? In the interest of time. Oh, I'm out of time. Next time. Thank you very much. We'll see you.